Hello and welcome to a pint of astrobiology. My name is Ben Pierce and I'm your host. I'm an astrobiologist and amateur brewer of beer, and in these pint-sized videos I will discuss the latest conundrums in the field of astrobiology over a pint. So let's dive right in. Today's episode is on detecting life on exoplanets via biosignature gases. Now, exoplanets, which are planets orbiting stars other than our sun, are light years away, really far. So we're not going to be able to travel there to detect life anytime soon. But that's okay, because we can detect life from here using telescopes and a technique known as transmission spectroscopy. Transmission spectroscopy involves observing a star while a planet is transiting that star. This is akin to, say, the transit of Venus you may have heard of, where you could see a shadow of Venus in our sun if you look through, say, a solar telescope, which last occurred on June 2012. Now, a planet blocks some of the star's light when it is transiting that star, and if that planet also has an atmosphere, the atmosphere is going to absorb some of that starlight as well. But the molecules in the atmosphere absorb very specific wavelengths of light. Therefore, if you look at the spectra of that star while the planet's transiting, or the light broken down by wavelength, you can see a certain signal in the starlight which will tell you which gases are in that atmosphere. How cool is that? Now, because we can detect the gases in an atmosphere of an exoplanet this way, perhaps we could detect gases produced by life on that exoplanet. This is what distinguishes biosignature gases from other gases in the atmosphere. Some examples include oxygen, which is produced on Earth by trees and cyanobacteria from the process of photosynthesis, and methane, which is produced by methanogenic archaea in the stomachs of cows, which is then belched or farted out by those cows. There are multiple other biosignature gases produced by life, things such as ammonia, phosphine, and dimethyl sulfide, but oxygen and methane are the ones that have built up most abundantly in Earth's atmosphere from life. So they're somewhat of a focus. Now, the main telescope that's going to observe biosignature gases on exoplanets is JWST, which launched just this past December 2021. But one problem that arises is that JWST is unlikely to detect oxygen, because oxygen really only has one narrow, weak wavelength band that is in the range that JWST's instruments can detect. But maybe JWST can detect a proxy species for oxygen, such as ozone, which would suggest that there's also oxygen in the atmosphere. Another problem is that a lot of wavelength bands for species, molecular species, overlap, such as you can see here. So scientists really have to pull a signal out of a messy spectra. Now, the more transits you observe, the cleaner the signal becomes, but you can't just hog all the observation time on JWST. Scientists have to share. We're good at sharing. But in general, I see the biggest problem is in being conclusive about whether a biosignature detection is actually produced by life and not some sort of abiotic source, such as, for example, lightning chemistry or UV photochemistry, or maybe some geochemical source such as volcanoes or hydrothermal activity. Now, atmospheric modeling can help sort out whether some of these abiotic sources can account for a biosignature gas, but you need specific detailed information about that planet in order to have an accurate model. Things such as the pressure temperature profile of that planet and the oxidation state of the planet's mantle, which will determine which gases are released from volcanoes. And these are things you can't really observe from afar. So I really don't think that there's necessarily a smoking gun biosignature that you can detect and say for certain this is produced by life on that planet. What you're going to need to do is follow up that detection with an extensive suite of atmospheric models for various conditions which are plausible for that planet. And then in the end, after all that modeling, I think it'll probably come down to a statistical argument. But I hope someday soon, someone will prove me wrong. That's it for today. Cheers.